All right, everybody. Welcome to today's seminar. We continue to improvise. Today's speaker will be Marija Tomasevic, who will tell us about connections between holography and
the sitter.
That's it.
Yeah. Okay. Thank you very much. And thank you so much for inviting me to be here. I'm having a lot of fun, and I hope to have a lot of fun throughout the next month. Even we're gonna have to wear masks and get mosquitoes and so forth, but okay. So if you don't hear me or something, just yell, because I have too many things on my head. They might fall off. It might be disastrous, but let's hope not. So today I'm going to be talking about the sitter through holography. And specifically, I'm going to be focusing on the three-dimensional case. So when I say sitter through holography, just to make it clear, what I'm thinking about here is the brain world setup, which we put as our brain to be a sort of a brain with the sitter asymptotics. And we're going to see why the three-dimensional case is specifically interesting. Okay, so this is a work in progress. We don't have all the answers yet. And it's work with Roberto Emparan, Juan Pedraza, Andy Suesco, and Manus Wisser, none of whom are here, at least not personally. I guess Roberto is online. But okay. So the rough outline of today's talk will be the following. So I'm going to cover these three topics. The topics are the sitter. So I'm going to talk a little bit about the basics of the sitter, the universe. Then I'm going to explain how we can put the sitter spacetime on a brain. I'm going to explain a little bit about brain dynamics, what constitutes them. And then we're going to see how we can make black holes in the sitter spacetime in the three dimensions. And these any sort of black holes, they will specifically be quantum black holes. And in the end, I will talk a little bit about some ideas relating to double holography and the sitter and its dual. Okay. So let's see why the world of the sitter in three dimensions is a desolate one. So to see this, let's start with something very simple. We're going to write down the Schwarzschild Dimensions. It's a very familiar metric. There's some sort of a mass parameter there. And we see that this metric allows for two horizons. The two horizons are the black hole one and the cosmological one. And we see that there is also a limit in which these two horizons are going to approach each other. This is called the Marija limit. And this is basically a limit where our black hole resides in the sitter universe, and it grows so big so that their horizons meet up. So that's the general story. Yes. I can repeat a question if it's a short one. Okay.
The horizons don't coincide in that limit. They just have the same size.
Okay.
So the topology, the spatial topology is S1 cross S2, and they reside at different places along the S1. And in the Marija limit, it just becomes a direct product.
Okay. Thank you for that comment. Okay. This is not really relevant to the rest of the talk, so that's why. But in any case, this does set a bound on the mass of the black hole that can be in the sitter. So that's one important thing to note about it. But we see that something funny happens if we go to three dimensions now. If we go to d equals to 3, we see that we lose the 1/r term, and we basically just obtain back a constant that depends on some sort of an energy. And we're left with just one of the horizons, the cosmological one. So let's see, what does this metric actually tell us? And we're going to do that by zooming into the sitter center, so to say, by looking near r equals to 0. We can rewrite the metric very simply. We can also do some very simple rescalings of coordinates, and then obtain something that looks very much like flat space. But it's not exactly flat space, because this angle is identified with 2 pi. It's identified with some conical deficit. So what does this mean? Well, first of all, this conical deficit is known to be understood also as a gravitational field of a particle mass at rest. Sorry for the patchy sound. we see that instead of black holes, what we obtain is just these sort of conical solutions in the sitter in 3 dimensions. So the way that I obtain this limit is by going to r equals to 0. So one can see that we also obtain the same solution in flat space in 3 dimensions. So one might ask the question, if there is a simple way to actually see that there are no black holes in 3-dimensional flat space or the Sitter spacetimes, then one might ask a question how we can see that this really had to happen. And I'm gonna argue that one can really see it through looking at scales. So in 3-dimensional gravity, the Newton's constant and the mass together make up a dimensionless product, so to say. This means that if we include a massive object into our theory, we can't make a length scale out of it. And if we don't have a length scale, we cannot make a black hole. So we need some sort of length scales in order to make black holes. And one way to introduce a length scale would be to add cosmological constant. However, we quickly see that even though cosmological constant adds a length scale, it's still not going to be enough to actually make a black hole. In order to make a black hole, one still needs unattractive potential. This is one way to see why ADS3 black holes can exist. ADS is sort of a gravitational potential, which is attractive. It has a tendency to make things collapse. And so we obtain a black hole. In contrast, if we go to the Sitter, the Sitter spacetimes basically, and they dilute gravitational interaction. So from here, we see that the best thing we can do is to form a cosmological horizon, not a black hole one. Okay. But because the cosmological constant is not the only way that we can introduce a scale. A nice way to introduce a scale would also be to introduce it through quantum effects. That is to say, we introduce it via H bars. Yes?
Stupid question. What's a cosmological horizon? How do you define a cosmological horizon?
How do I define a cosmological horizon? So if you go to the metric that I just showed before, there was basically a constant minus r squared.
Mhm.
That solution equal to 0, that gives you the cosmological.
Okay, maybe, what does that physically mean? Like, am I supposed to think about it?
The region behind the horizon is non-compact.
Okay, okay, yeah, thank you.
Okay, I didn't hear that, but I'm guessing you answered the question.
He's asking what the difference between black hole and cosmological horizon.
Yes.
Okay, well, there are many sort of differences. I guess one can say one hides a singularity, for example. The other one does not. The one expands, the one is an object in space. You can study properties of both thermodynamically, but both constitute different objects when you start studying them.
Okay, yeah, yeah, thank you.
Sorry, that was a very, I don't know if that was answering your question. Okay. So as I was mentioning, cosmological constant is not the only way one can introduce a length scale. We can introduce it by introducing a Planck length. However, having a Planck length is sort of telling us that we're going to have Planck scale black holes. So that's not very interesting. We can see that if we add a large number of quantum fields, we can have a larger black hole. So here we see that we can introduce some sort of parameter C, which is basically going to be the central charge that is very large. And it basically constitutes the number of quantum fields that we have in our system. And one can see that with the C of much greater than one can have semi-classical black holes. Yes?
Why is the first of these not interesting and the second one is?
Well, it's not interesting in the sense that you're making Planckian black holes. You want to make something that's valid very much semi-classically. I want to make a large black hole.
I'm thinking the number of fields like this will help with that. Because black hole evaporates much faster when you have a lot of fields, so it still evaporates as fast as it forms.
Well, we're going to see what is the sense in which I meant a large black hole and why is it interesting. It's on the next slide. Okay. So if one really does of quantum fields on top of a three-dimensional spacetime with a defect, one really sees that one obtains a horizon. And so here you see that, I guess this, yeah. Here we have, I introduced the length of the cosmological again. We have this new factor here in the metric that basically scales correctly as 1/r, as we needed in the usual case of Schwarzschild de Sitter black holes. And we see that there's some sort of a factor f of gamma, which is related to the stress tensor of the quantum fields that we have introduced into our spacetime. So this is a calculation that one can do exactly. It's a conical defect spacetime, so one uses different methods, but one can obtain the solution. And you see here that really this stress tensor is the thing that gives us the horizon size of the black hole. So from here you can see you have a small effect, you're going to have a smaller black hole, have a large effect, large. In that sense, it's going to. So that's what I want to say. Yes.
When you say that this is an exact solution, that means this is like a
Linear.
non-perturbative.
No,
Oh,
no,
it's
no.
linear.
Sorry. Yes, you solve the linear equations.
Well, but when you say linear, like linear in H bar, it's the semi-classical Einstein equation,
Yes.
and it's an exact non-perturbative solution of that.
Sense. I just
Oh,
meant
okay.
you computed the conical defect. Just G mu equals 0.
Are
T
you
back
doing?
reacts.
Are you doing all orders in back reaction or just one order in back
Not.
reaction?
Here, no.
Okay.
This is just a one loop, if you will.
Okay.
Question?
Yes.
Usually in a higher dimension, if you have large number of field, G Newton times number of field gives string length, right? Because if you make, this is a kind of follow up with Raphael's comment, that if you have many particles, then it gives a large radiative correction to Newton's constant. So the cutoff of the field theory must be lowered accordingly. So usually string scale is separated from a Newton constant by square root n or n. And why you can avoid this case? Oh, of course, because gravity does not have a propagating degrees of freedom. So 2+1 dimension is special in that sense. But are you sure that this can be treated in semi-classical analysis?
In this case, in 3 dimensions?
Yeah.
Or in general?
Higher dimension, it's not, clearly not. I mean, people know that string length scale with the number of low energy field in unit of Planck scale. So you increase number of n won't help like cutoff. So yeah, here it is okay. Yeah, why? Yeah, that's the question. Of course, propagating degrees of freedom is not there. So that's the huge difference. Is that reason? Or namely 2+1 dimensional gravity is UV complete. Is that what you were kind of?
I'm not quite sure that I got all of the things that you were saying, but basically here, I'm just doing a very simple calculation here. This is just the usual Birrell and Davis calculation of a back reaction, so to say.
Yeah, it's a classical, but I'm talking about quantum. Yeah, quantum thing.
You're talking about, sorry?
Quantum. I mean, classically everything's fine, even in higher dimension.
So you're concerned that this is not going to be okay?
Or a cutoff regime. In higher dimension, I expect scale you're looking at is a cutoff regime. But I'm not sure. The same argument doesn't apply to 2+1. I'm aware, but I just want to know whether you kind of checked or whether, yeah, are you sure or not? Yeah.
Okay, Roberto, maybe you can.
Yes, I can say. So in this case, it's not difficult to verify that even if the scale of the cutoff is lowered by having a large number of fields, you can still have black holes with a size which is much larger than the size of the cutoff. It's a simple calculation. I cannot reproduce it now, but I can give it to you later if you want.
Oh, so the scale is actually bigger than G times N, the size.
So the scale of the cutoff, I mean, it's not just the Planck length.
Yeah.
Yeah. You can have, yeah.
But black hole is even bigger.
You can have the black hole even bigger.
Oh, okay. Okay.
Yeah.
That I didn't get it.
I can give you a reference for that.
Okay. Cool. Thank you.
Okay. I think I got like 30% of that. Sorry. Yes.
Maybe this is obvious to everyone else, but can you just say a few words about where the second equation comes from? How do you know what the stress tensor's expectation value here?
This is something that you impose, basically. You solve for a conformally coupled scalar field. So you know what the stress tensor has to look like. You use deficit space-time, and you
Oh,
can solve this exactly. Well,
So
sorry, that's not the correct word.
the conical deficit is sourcing the scalar field?
You are putting on top of this space-time a conformally coupled scalar field.
Right, but how do you
Yeah.
know what so this is this is like a classical VEV that the scalar field has in this background? Is that how I should think of it? No.
Matt, it's a static space-time, so it has a unique vacuum state. And so this is the expectation value of the stress tensor in that vacuum state.
Yeah.
I see.
So it's just, it's like
yeah.
a totally closed calculation. It's self-consistent.
That's why I mentioned the Brill and Davis sort of quantum fields and curves and type of calculation. Okay. Yes.
Okay. One question, just because you said yes to what John said, I would have thought that you're just computing perturbatively in GH bar,
Yeah.
and you're including the first quantum correction and then solving for the metric again.
Yeah, exactly. Sorry, is that
So
not what you
it's not to infinite order in GH bar.
No.
Yeah.
It's the one loop correction.
Yeah, it's one
I
loop
did
correction, and
say
then
one loop, yeah.
you include that in the metric. An unrelated question is, this is kind of to everybody, your microphone cutting out.
Okay.
Would it make sense if we give you one of the question microphones, because they don't seem to be doing that?
Okay, yeah, I can do that.
You're gonna have to use both hands, but
Let's see how it goes.
should we do that? Sorry? I mean, it seems to be cutting out all the time. I don't know.
It's gonna be much more simpler for my head. Can you help me
yeah,
out
you're
with
in
this?
trouble.
Okay, it's a breakfast and a show, I guess.
Yeah.
Hello? Okay. Welcome back. Okay, let's continue. So this is a perturbative calculation, as we just established. And as a perturbative calculation, it can only be trusted perturbatively. So what we want to do is to put this quantum induced horizon, because we saw that this horizon comes from quantum effects, we want to put it on a stronger footing, so to say. Usually that would mean that we have to solve all these equations, sort of a coupled system, metric plus quantum fields. But what we're going to do instead is to put this de Sitter 3 spacetime on a brane, and in this way obtain all orders in H bar, with a caveat that it's at large n. Okay. So branes, usually known as end of the world branes. I'm going to go through them now, but I just wanted to see if this looks familiar to anybody. This is the end of the world.
Yeah, that one is on.
Ah. Okay. So this is the end of the world in Norway. It's not on the top of the Norway, as you would expect. It's at the bottom. But nevertheless, we're going to continue now seeing what is the physics of branes. So let me just tell you a little bit about the general philosophy. We're going to do it a little bit quickly. So the general philosophy is that we have some classical dynamics in some sort of an ADS bulk, and it's going to perfectly encapsulate all the quantum dynamics of the dual CFT. This is just the ADS CFT statement. But now the part of this boundary has been pushed into the bulk, looks like a brane, and therefore our CFT couples to gravity on this brane. This is something that has been explained by this paper, 22 years ago, Neharos, Skenderis, and Solodukin. And here I'm just going to review some of the basics of this brane construction. So putting the brane and the bulk basically corresponds to integrating out the UV degrees of freedom of the holographic CFT. We're going to see what that means. But this CFT below this cutoff is going to give a rise to some sort of a stress tensor. And the stress tensor is going to have a large central charge, like I was mentioning before. And it's going to play a big role in determining the size of our black holes in the sitter. And crucially, this bulk solution, so the ADS bulk, is going to encode all of the quantum back reaction of the CFT on top of this brane. So what are we going to do in ADS4? Because I want a three-dimensional brane. I'm going to start with ADS4 and look for some sort of a time-like three-dimensional hypersurface that has an extrinsic curvature proportional to the induced metric. We do this in order to have a purely tensional brane. So to have a brane that only has gravity induced from the bulk. We then cut our spacetime along the surface, throw away the rest, and glue an identical copy on top of it. And of course, gluing things on top of things that don't match up perfectly induces some sort of a discontinuity in the extrinsic curvature. We can see what is this extrinsic curvature doing now using the standard Israel junction conditions, which are then going to give us a stress tensor on the brane. Yes.
Okay, so going back to the slide before, let's view this as a proposal as opposed to a thing that's, you know, completely uncontroversial within EDS CFT. So what is the status of this proposal? If I remember correctly, it's been verified at one loop in the context of ADS5 times S5 and n equals 4.
Okay.
But, you know, what is the status of this proposal more generally?
You mean from a top-down perspective?
Well, from any, it's an open-ended question. So.
All right. It's a fair point. The way that I'm approaching it here in this talk specifically is going to be more bottom-up than top-down. So it's to say, I just start with sort of a bulk. I know how to do this procedure exactly. The procedure, I think, is fairly well explained and understood, at least when the brane is very close to the boundary, so that you don't get any higher curvature corrections. And then we're going to just see what this implies for qualitative features of the things that I'm going to talk about on the brane. Now, when we want to talk about the UV completion, that gets a little bit tricky. I honestly don't know. I don't think there's anything very well established. So I would be very eggshelly around that. Yeah, it's a fair point. Okay. So we got to this stress tensor that we got from the extrinsic curvature on one side minus the other side. We know how to do this. We can obtain the stress tensor now exactly by using the condition that the K mu is proportional to H mu. But we can also obtain the stress tensor as from an action characterized by some sort of a tension. So this tension has something proportional to 1 over L. And this 1 over, well, this parameter L basically sets the distance of the brane to the would-be boundary. So remember, I had some sort of a ADS spacetime. I cut out a piece of it, out the rest. So there is a place where the would-be boundary would be, and L sets the distance to this would-be boundary. It also tells us something about the acceleration of this brane in the spacetime, which is something that one can have a very good intuition for, and I'll try to explain it a little bit later. So that was obtaining the brane. How do we see now getting the gravity on the brane? Well, what we do is go to the bulk, take the Einstein-Hilbert action, take the GHY term, and we sort of integrate out along the radial direction until the brane. And this is a procedure that holographically corresponds to integrating out the UV degrees of freedom. We're sort of IR UV, we're throwing out the IR in the bulk, throwing out the UV on the boundary. And this procedure leads to the induced gravity on the brane. The gravity action has this sort of a term. Yes, sorry.
I just want to make sure I understand sort of the basic setup. So I've understood, from what I've understood, this thing where you were talking about finding a surface with a particular extrinsic curvature and doing this gluing, the goal of that was to give you a three-dimensional spacetime that had a particular delta function stress energy source. So it's a solution of Einstein's equations with a delta function stress energy source. Okay, so I'm happy with the fact that we have a particular solution of Einstein's equations, but it seems like you're going from that to talking about a theory of gravity with particular parameters or particular behavior, and I have not understood the connection between those two things.
Okay. Are you familiar with the Pfefferman-Graham expansion?
Yes.
Okay. So you know how usually in ADS-CFT we would do the Pfefferman-Graham expansion to some sort of a regulator surface. We would see stuff diverges. We would introduce counter terms to get rid of those divergent terms. They're basically the non-normalizable modes that go all the way to the boundary. That's why you want to get rid of them. So here, what you do is basically the same, except that you want to remain at this regulator surface. The regulator surface is the brain.
So
You don't want to introduce any counter terms, and the non-normalizable modes that would usually give you problems are now normalizable because they're at the finite distance from the boundary. So this is, sorry, just finish. These normalizable modes, so to say, are the things that induce gravity on the brain.
So would it be accurate to say that what you're doing is you are quantizing the field theory of metrics that are consistent with the brain boundary conditions in the same way that in ADS3 we'd be quantizing the space of metrics that are asymptotic to ADS3? Here you're quantizing the space of metrics that are asymptotic to this brain.
Why do you talk about quantizing? I mean, this is a purely classical, so to say, procedure.
Oh, okay, but you're talking about a phase space of metrics that have this brain boundary condition?
Right.
That's correct. Is that what you mean by the induced gravity theory?
Space of metrics that have. Yes. Okay. So this procedure, which can be outlined in many more details, I just haven't gone through them basically, gives us some sort of an effective action. And from this action, one can see various parameters emerging. So, well, one can see how to identify the parameters that are relevant for the brain dynamics. So we can see how the three-dimensional Newton constants emerges. We can identify the term in the action as a sort of a cosmological constant term. So all of these things can be done very much exactly. Let's see a little bit more pictorially what this means. And in particular, let's see what actually says the brain asymptotics. Because here I was just very sort of nonchalant. I wasn't talking about any specific asymptotics. And I want to give you what my intuition is for this. I don't know if it's going to be very intuitive for you, but let's see. So we can phrase all of these different cases in terms of the acceleration parameter, which is also the parameter that says the distance to the boundary of the brain. And one can think of this acceleration parameter as the following. If I have sort of weakly accelerating brains in this ADS spacetime, these are going to have ADS or flat asymptotics. Strong acceleration, in some sense, is going to give us the de Sitter asymptotics in the brain. One can think of this basically as being sort of very far away from the Rindler horizon in some specific sense, or accelerating fast enough so as to see the bifurcation surface. This is just an intuition, but what this actually gives us is three different scenarios and three different pictures one can draw. So the first picture here that we have, this is the case where we have an ADS brain. You see that it hits the boundary at two different points. And all of these dashed curves are the things that we threw away, okay? Okay, so that's very slow acceleration. Slightly faster, but not too fast, is the case of flat brains. So this is a case of a flat brain. Doesn't look too flat, but if you were to actually draw the full cylinder picture, which I can do later on if you want, you will see that one obtains literally the Minkowski sort of a spacetime, well, asymptotically flat spacetime for this brain. And finally, the thing that's going to be of interest to us mostly is going to be this case here, where we see that we basically cut out all of the boundary in some generic time slice, and we obtain the smaller circle, which has the Sitter brain asymptotics. The horizons in the cylinder picture would be more sort of illuminating, but I didn't have time exactly to draw them. But one can imagine them going and cutting this brain in a sort of an X direction. We'll see a little bit more later if I can get an intuitive picture. Okay, so that was the general story. Now we want to actually be in a specific setup. So for that, we're going to specialize to something called the ADS4C metric. This is a sort of one of the solutions of Plebanski-Demiansky metrics, if that means anything to you. It's not extremely important. What's important is that this ADS-C metric is chosen because we can obtain black holes in the brain in a very simple manner using this metric. So here, just to give you some sort of intuition on these parameters, the mu parameter can be interpreted as the mass of the black hole, and L, as before, is the acceleration parameter. So that's our ADS for spacetime. What we want to do is now cut the spacetime with some sort of a brain. We find this brain that satisfies the k mu proportional to h mu condition at x equals to 0. And the metric that we obtain on the brain is obtained like this one. I keep pointing there because it's easier. I hope it's okay. Okay. So we see we obtain basically a three-dimensional Schwarzschild-like metric. We see that there's exactly two horizons like we wanted, one here and one here. And it looks very much like the four-dimensional solution. If you were to go back to the first slide that I wrote, there was a 1 over r d minus 3. D equals 4 gives us exactly this form. And this is exactly fine. We obtained our solution as sort of a section of a four-dimensional black hole. But also notice that this form agrees exactly with the perturbative calculation. The difference here is that now we have the validity of the solution much higher than the perturbative calculation. So remember, the perturbative calculation is a one loop. Here we basically have all loops. This is what the brain gives us. But the brain, of course, is a thing that we obtain from a large n CFT. So this is a thing that exists for a large n. So this is perturbative in 1 over n. Yes.
Yeah, that might be a bit of a silly question, but I mean, usually if you want to like talk, double holography and those things, you want to have your brain close to the boundary, like you said before, because you get like localization of your graviton modes and so on. So this x equals to 0, is that generic? Is that such a location? Like, do you get localization there, or?
So the thing that sets your distance is this parameter L, and you can still move it around. The section is just along x equal to 0, but now you have to go actually in the correct conformal frame, so to say, to get to the actual boundary. So parameter L is really what you're looking for in order to suppress the high curvature corrections. If that's
Okay, yeah.
It goes as L square, and we're at a linear order in L. Okay. So because of this large n sort of a comment, we can say that brain dynamics basically resummed all of the relevant iterative procedure that we would have done in this very difficult case. So G mu equals T mu, solve again, blah, blah, blah. That's all solved directly in this brain model. Okay, so we obtained the black hole, and it's a black hole in the sitter 3. So what can we do with it? Well, we can ask some questions about it. For example, we can ask, what are the properties of these quantum black holes? We can calculate mass, entropy, temperature, doesn't really matter what. For instance, we can also calculate what is the Marija limit. Maybe that's of interest to you. We can see that the basic GTT factor has three roots. One of them is unphysical, 2 are the black hole, the cosmological horizon. The distance basically of this curve with respect to this y-axis is set by the mass of the black hole. So we see that these two solutions are going to sort of pop down for a very specific mass of the black hole. That is the one that is the largest one that can fit inside this sitter. What does this tell us about the CFT? Well, it basically tells us that as the Marija limit places a bound on the mass, it also places a bound on the back reaction of the CFT. Basically, we cannot have too big of a back reaction. We're going to make a black hole that's too big. Okay, this is one thing one can ask. Another interesting question, at least potentially interesting, is regarding something that maybe you wouldn't have thought about in the beginning, which is the probability of this de Sitter horizon to pop out a small black hole as a sort of a fluctuation. So this is a calculation that was done by Susskind. And the reason why it's interesting is because he used this calculation in order to conjecture a tentative dual of de Sitter spacetimes in terms of matrix models. So I'm now just going to go slightly through his very simple calculation and see how things change in this case. So calculation is pretty straightforward. He works with black holes in de Sitter spacetime. So the simplest one in this case is going to be the 4-dimensional case, the classical one. So we're going to start with the pure de Sitter in 4 dimensions and calculate its entropy. It's just basically its area of the horizon. And now one can talk about these fluctuations in which we're going to decrease the entropy by emitting a small black hole. The probability of that happening is going to be given in some sort of an exponential of an entropy deficit. Everything very simple. So in order to calculate the entropy deficit, we want to calculate the entropy of the small black hole. The small black hole is very, very familiar. We know how it looks like. And so this shrunken entropy of the de Sitter horizon is going to be given by the shrunken area. That is to say, instead of R, we have R minus the mass of the black hole. And we simply calculate what is the entropy associated to now this shrunk de Sitter horizon. In doing so, we now see what is the entropy deficit, and we obtain some result. Doesn't really matter what it is. But what does matter, and this was really Susskind's point, is that one can rewrite it in this very simple way, as a square root of a product of 2 entropies. I keep echoing, I don't know why. Sorry. So the big S here is the entropy of a de Sitter, pure de Sitter. Small s is the entropy of a 4-dimensional Schwarzschild black hole. So what can we learn from this extremely simple exercise? Well, we can argue, that is, Susskind will argue, that this entropy deficit can be reproduced only by sort of a matrix model that can be tentatively dual to the de Sitter spacetimes. So let's see why. So first, we're going to assume that this matrix model is basically comprised out of horizon degrees of freedom. So horizon degrees of freedom can be sort of put in n cross n permission matrices. And then we can talk about the total entropy of these matrices in a sort of a thermal equilibrium. The total entropy is going to be proportional to the total number of degrees of freedom, which is n squared. And the proportionality constant is going to be given by the entropy per degree of freedom. Again, very simple. A fluctuation in this matrix model is going to be given by some sort of a formula like this. So it's just the extension of what I was talking about before. And this fluctuation is going to represent the black hole analog on the space-time side. So now we're going to be motivated by matrix theory in general. And we're going to assume that this state of just the de Sitter horizon popping out a small black hole is well separated in this matrix model, in the sense that we can suppress the off-diagonal degrees of freedom, put them in some ground state, and therefore only care about the diagonals. Just to have some sort of picture in mind. All of the things here and all of the things here are the only things that are going to matter. So we split them into block diagonal forms, yes. And we obtain the entropy.
Just to be sure that I understand this, right?
Yes.
So like each of these blocks correspond to degrees of freedom on one of the horizons.
So this here is the de Sitter that has been shrunk down by the black hole.
Okay.
And this is a black hole. So just like in the spacetime case, this is just a matrix representation of them. And we can simply add the entropies to the state. We obtain something like that. And then we obtain a very similar formula for the entropy deficit. This is what Susskind then argued is the only way to obtain this sort of a square root behavior in this 4-dimensional setup. One can also generalize this formula for any number of dimensions. And what comes out as a sort of an endpoint of the calculation is a formula like this. Now, for me, it doesn't really matter what this formula is. What I do care about is this fact here, that the small s has a d-3 in its exponent, and therefore vanishes for classical 3-dimensional black holes. So one can ask, how does this calculation that Susskind just did change once we include quantum corrections and now we have quantum black holes in the story? So quantum black holes, not classical. We can just redo the whole computation, calculate the relevant entropies. But of course, instead of going through the details of the calculation, I'm just going to lay out what is the idea that you should have for what to expect as the end result. And it's basically going to be given in terms of the doubly holographic perspective. Okay, so what are we supposed to expect in this case? We have our de Sitter 3 brane, and we know that it's dual to everything inside the ADS4 bulk. And the de Sitter 3 brane is going to have some sort of an entropy. It's going to be generalized entropy, and it's going to be dual to the usual classical entropy in the 4-dimensional bulk. This is basically just the usual ADS-CFT statement. So S4 here represents just the classical entropy. In this case, is going to be given by the sum of the both horizons. And S3, we see that has this additional component of the von Neumann entropy that lives on the brane. This von Neumann entropy comes from the CFT that lives alongside this black hole inside the Sitter 3. So we see that basically, we're going to get some sort of 4-dimensional results. We have our entropy that's 3-dimensional. It's going to be corrected by the quantum fields into a generalized entropy. And technically, what this gives us is a 4-dimensional result. So what this means is that once we account for these quantum corrections in Suskind's proposal, we're going to go from something like this, where our 4-dimensional results give us a square root behavior, to something like this, where we have a 3-dimensional result in the generalized setup giving us the same square root behavior. And this is something that one can verify by an exact calculation. Therefore, we can we can conjecture that the conjecture will be modified in a very specific sense. We're no longer going to have some sort of factors like these ones. We're going to have them modified in some specific way. So all of this was, yes.
Thank you. So wait, can you, so wasn't the idea that like once you get these, you could relate it to the 4-dimensional entropy?
Right.
So what, yeah.
So the reason why I was relating it to the 4-dimensional entropy is because this is a doubly holographic perspective in which you have everything on the brane being encoded by the classical bulk. That was kind of like the first sentence of the general philosophy slide, if you remember. So all of the entropy that I have on the brane is going to be given by all of the entropy that I have in the bulk, and everything that I have in the bulk is basically just 4-dimensional usual entropy.
Thank you. I see that's being used over here, but I'm not really sure how. Like in your last statement, when you're saying, okay, I have this conjecture originated by Susskind and I'm sort of modifying it to this, I don't think I see how you're using that information. Maybe it's straightforward.
So you see that there is this square root behavior. That square root, Susskind would argue, is only valid for the 4-dimensional calculation. I'm now saying that if you go to 3 dimensions and include the effect of quantum fields, you obtain the 4-dimensional behavior that he was talking about. So the coefficients that go here cannot be the same, right? Because now I have sort of a d-3, it's going to be something non-zero. So first I have to modify for that. But also the coefficients themselves cannot give me the same type of a square root behavior anymore, because now I have the effect of quantum fields. Yes, there is still a delta S3 is what he said. Yes, that is true. This is now a 3-dimensional calculation. One can do this calculation for this deficit entropy. Sorry, the entropy deficit calculation, one can do it exactly in this 3-dimensional setup. And one really sees that one obtains a square root behavior. Here, I didn't go through the calculation. I was just arguing why you should have expected this from the beginning.
Okay, yeah, I think I get it.
Okay.
Yeah, thank you.
Yes. Ah, smart. Okay, so I should just do it like this, no? All right. It's almost the end, but okay. Okay, so this was a
Maria,
very, yes.
sorry. I didn't understand whether you're saying that you're using, are you using double holography to compute the entropy of these black hole configurations on the brain? In other words, you're computing a classical RT surface area in the 4-dimensional geometry?
So what I was doing here was just to argue through double holography that this is something that maybe you should expect. What we actually do in the paper is calculate these entropies.
I'm asking how do you calculate a classical RT surface area in 4 dimensions, or
Well, we
you're able to do
yes.
this directly on the brain, or both?
Well, we don't know how to calculate the CFT entropy basically, so you have
Right.
to use a double holographic perspective.
So you're getting these entropies from the classical RT surface in 4 dimensions.
Yeah.
Thank you.
Well, just classically, you add the horizons together. Yeah. Okay, so this was a very simple exercise that one can do. But the basic point here, I guess, that I want to emphasize is that if you want to use entropies in your calculations in order to find some sort of duals, the lesson that we're learning here is that one should really include the effect of quantum fields as well. It's not enough to consider just the classical effects of black holes and horizons. One really has to include the quantum effects as well, because they can qualitatively change the behavior of whatever your tentative dual is. Okay. Now, that was just one way to see what kind of a dual we can have for our de Sitter spacetime. But maybe we can exploit the system that we're in, that is to say the brain worlds, and see if they can tell us some sort of hints about what can the tentative dual of de Sitter really be, instead of simply conjecturing some sort of matrix model or whatever. So can we see some sort of hints? In order to see some hints, I'm actually going to go for a second back, not to the case where I have de Sitter brain, but I'm going to have ADS brains. So I'm going to go to the case where I have this picture. Okay. For the Zoom people, I don't know if you see this. I only drew the ADS brain. So what can we see from this ADS picture? So here we have this brain. This is the ADS brain. This is the 4-dimensional bulk. And we see these little 2 dots that I drew. These 2 dots are basically defect CFTs that live on the boundary. So they're co-dimension 2 objects with respect to the bulk. And they're coupled to the bath CFT that we usually call the CFT in the ADS CFT set. Aha, yeah. Okay, sorry. I forgot about this. Okay, good. So we have the picture that I just drew. In the cylinder sort of representation, we have this very nice picture here, where I just extended in time this brain. So this is the brain that it's time-like. I threw away the rest of the cylinder, and all we have is this part of the cylinder. Okay. So what do I mean by these defect CFTs? I just want to put everybody on the same footing. Maybe I should have done this in the beginning. But the idea of double holography is very simple. So we're going to have some sort of a defect CFT coupled to a bath. That's the first level of holography. We have the second level where we now dualize this defect CFT as a sort of an ADS spacetime. It's a defect CFT, so it's also going to have some sort of a CFT D+1 on top of it as well. You can think about it as degrees of freedom of this CFT sort of spilling over onto this brain. And finally, we can represent both of these CFT D+1s as their ADS counterparts. So as a purely gravitational picture. So that's the case for an ADS brain, as we can see here. So now we see that this brain is sourced by the defects. And so we can take some sort of a leap of faith and say, well, maybe all brains in the sense are going to be sourced by some sort of defect. What does this mean for our de Sitter brain then? Well, we see that our de Sitter brain doesn't really hit the boundary anywhere in this generic slicing. But actually, if we drew the whole picture, we would see that this slice here is actually just a simple slice here. And what we have is a full hyperboloid going, expanding like a good global de Sitter brane would do, and hitting the boundary at some sort of finite boundary time. So this is the picture, these little lines here are things that I throw out. So this will be the would-be boundary of ADS. I just sort of squeezed in the cylinder at some point, and that squeezing in, that brane is basically the de Sitter brane. So as before, let's take a leap of faith and say, well, my brane is sourced by some defect. This is obtained where I hit the boundary. So I see here that the defects would be living at asymptotic infinities in the past and in the future. And they would be Euclidean defect CFTs. For some of the more experienced, I don't want to say older members, this maybe gives you a strong hint that something like DS CFT is the correct dual picture for the sitter. I say correct because who knows, this is the bottom-up model after all and so forth. Well, let me just emphasize that there is one difference, at least right now, that we see with respect to the usual DSCFT proposal. And the difference is in the fact that the DSCFT proposal has only one slice. Here we have two. We have the initial state and the final state. And they both sort of source this de Sitter expanding universe in between. Okay, so that's basically all that I'm going to say about that idea. I would love to discuss it if you have any thoughts. But for now, I'm just going to summarize what we've done. So what we managed to do is to construct a black hole in 3 dimensions in de Sitter space. And one can do exactly the same calculation for flat branes as well. Simply by using this brane formalism and noticing that these black holes come as results of quantum effects. We can compute all the usual thermodynamic properties, which I haven't shown you at all. And we can maybe answer some potentially interesting questions, whatever you are interested in, really. And maybe we can try to understand what is the tentative dual that one gets from this brane wall perspective. And from that, we have filled out our desolate universe of de Sitter and made a little black hole inside of it. So thank you very much for your attention. Yes, ma'am.
Hi, so I have 2 questions. The first one is sort of more, maybe a little more technical. So going back to the earlier part of your talk where you found the back reacted solution via basically via ADS CFT versus the perturbative solution, both with a large number of fields, but in one case weakly coupled or free, in the other case strongly coupled.
Basically.
So why, I mean, is it surprising that they ended up being the same? Is there some non-renormalization theorem going on, or is there a more general phenomenon here? It just seems very surprising, right?
That they have the same form?
Yeah. Is it special to this particular setup somehow, or?
I don't think it's special to this setup, actually, because one can do well, let me retract that. It's maybe special to the fact that you have ADS4 and 3-dimensional branes, because one can do the same type of a calculation for, as I said, the branes which have ADS asymptotics. And one can see that one induces the same type of 1/r terms in those cases as well, and also in flat cases as well. So that 1/r really seems to come from the fact that it's a generic feature of all quantum effects. And you can also think about it, this 1/r really comes from the fact that you now created a black hole. So you're covering up conical disks.
I mean, is there some just dimensional analysis that forces it to have this particular form, and then just the coefficient, you know, depends on the theory or something like that?
Probably yes. Probably there's a very good way to see this, but
Okay. So
yeah, I would have to see that.
Okay.
Yeah.
Can you go back to your picture of the double holography with the de Sitter as this like hourglass? Yeah, so now if I take the middle level of double holography, then I have the defect. I have what is basically an ADS dual of the defect CFT, if I understand correctly, and that's the boundary. There are 2 of them. So for the final slice, it's the boundary of the ADS4 going up to future infinity.
Do
I have the picture correctly?
Yes, I think I'm understanding, but let me maybe draw just for the sake of being. This is very badly. So the purely the first level, so to say, picture is gonna look like this, so to say. Where this here is my CFT3, and this here, and this here. Well, this is also CFT3. This is the CFT2, which is Euclidean defect.
Right.
So that's the first level. The second level is just this, where I now have this brain instead of the defects.
Mm-hmm.
And the third level is just the same picture,
Filled in.
but I just look at the ADS part.
Right. So, well, I guess let's look at the first level then. So I have a Euclidean defect, two-dimensional defect CFT. So I shouldn't think of the I see. Okay. I guess the thing which is confusing, but maybe it shouldn't be confusing, is that now this guy is time-like, whereas in the usual double holography setups, that would be a spatial direction.
It's extremely
Yeah.
confusing. I agree.
But then, I mean, maybe it shouldn't be. Maybe it's just preparing a state, you know, via a Lorentzian path integral.
I've tried to understand it in very different ways. I would love to discuss this offline much more. I will have to say though that I don't have a full understanding still. We can sort of understand why it has to be Euclidean CFT. Really, the asymptotics of the sitter is, I would think, the most sensible place to put such a dual. So this is the picture. This picture actually emphasizes that. That's really where sort of gravity goes. You know, asymptotically, you approach something that you might call a boundary. But the actual CFT interpretation on the boundary side, I have no idea. Like maybe you're sort of just doing some sort of an overlap. Maybe it's just one number that you get. Maybe this second part doesn't really exist. There's also some reasons to believe that. Maybe there's a singularity above these two things. So maybe this Euclidean CFT cannot be coupled to this Lorentzian part. I'm saying all of these things because these are all the problems that I've encountered, but none of them exactly understood.
Right, but it could be something like.
Can I? Oh,
Yes.
Wait,
sorry.
finish my.
Yes.
Yeah, I mean, it could be something like a matrix element that essentially there's like what you might call an S matrix, which is represented by the de Sitter part.
Mhm.
And then you're just computing the matrix element in the state prepared in the bottom part and the state prepared in the top part of this operator.
It could
And
be.
that's the
Yeah.
number.
Yeah, exactly. It's just a number though. Yeah. Yasunori?
yeah. I think in an intermediate stage is you can relate with what we have been doing. For example, if you have like an anti-de picture, you have like a two defect and you have a bath, okay, surrounded by the two defect. Okay, and you go to the flat space, the defect collapse into one. And you can imagine that this moving this defect into the bulk. So that makes this is a co-dimension 2 from bulk's point of view. So from the de Sitter spatial configuration, it's a horizon. But because now you are moving out of the boundary, so this is a theory with gravity. So you can think of this is a holographic theory living on a stretched horizon, and that theory has a gravity. And now you can pull this. That's still living in a time-like direction. That's something we have been doing, and then also later, yes, people had a similar thing, including Lenny. But now then you can follow this like the theory with the gravity, living on stretched horizon, and towards the future and past in time direction, and then you can decouple gravity. So that's what you were saying, like living on a. And your brain configuration is great because if you push to the future in time and the past in time, you will approach ADS horizon. Sorry, ADS boundary. So you see the gravity decouples. So you can have real holographic theory without actually having gravity. Not like something like a Randall-Sundrum, the Planck blend thing. That's an intermediate holography. And then you can probably go more like decouple in a time like future and so on. That may be related with the state preparation and so on, usual DSCFT type thing. I think this is interesting. We can talk offline, of course. Not today. I'm somehow stuck at hotel, but yes. Yeah.
Okay.
Yeah.
I hope you
let's
get
just try.
unstuck within the next 4 weeks.
Oh yeah. I'm not too sick. I mean, I'm just today is something to So let's chat later. Yeah. It'll be fun. Could be fun.
Sounds good. I will just make one note. This is still though the usual Karch-Randall setup. So we didn't use anything new here. All of this construction could have been said like 20 years ago, basically.
Yeah, maybe. Yeah.
It's and people have considered these de Sitter brains and so forth. They use them for different things. It's simply that we didn't see anywhere emphasized in the literature, at least that we know of, that one can maybe give this interpretation of Euclidean defect CFTs. So that's the sort of a new.
Yeah, because you really like moving off like a speculative directions. I could even go like pinching off and move into the bulk, and then you can say intermediate stage you have horizon theory with gravity. I think that was probably not explicitly said in that way. So
okay. Well, I would love to discuss more in any case.
The setup was discussed. Yes, true.
Can you show those solutions? Those solutions are very interesting once it comes purely from quantum corrections. Can you show the slide again that has the
metric?
Yeah. So I guess I have a couple questions about these. So one is, I mean, this looks like a sort of standard static patch type version of the solution. So would I be correct in assuming that I can get a maximally extended t=0 slice or time symmetric slice by just doubling this piece the way we normally would? And it would again have topology S1 cross S2 like it normally does in Schwarzschild Dimensions. Or excuse me, it's 1 cross S1 since this is 3-dimensional.
I think so, yes.
And what controls two things? One is the size of the black hole horizon, and the other is what controls the smallness of the further quantum corrections that various people and I asked about at the beginning.
Yeah.
What is the small parameter for that?
So it's literally all answered here in this term. So this is the term that gives you the actual black hole horizon. Mu plays the role of the mass. One can see that exactly. I can show you if you want the actual equations. And L is this parameter that tells further quantum corrections. So if you will, we are only doing this.
Can you remind us what mu and L are in terms of other fundamental, like the number of fields that you turn on, or the Planck length, or what are mu and L?
So mu and L are basically the same thing as F of gamma that I was showing in the beginning of the slide. So it's some sort of a form factor that goes in the stress tensor that you're specifying from the CFT. But the parameters in that F of gamma come solely from the 4-dimensional bulk. And from the 4-dimensional bulk perspective, these parameters are exactly what I said. So L is the acceleration, and this is the mass of the black hole in the bulk.
So from the 3-dimensional perspective, how many things do I get to dial, right? I get to dial the number of fields or the central charge. Mm-hmm. That's one thing I get to dial. But you have here two parameters. What's the other thing I get to dial?
L. But L
yeah, but what is L?
So L can be two different things. You can think about it as the acceleration parameter. I forgot to mention this ADS4 symmetric.
So it's the cosmological constant from the 3-dimensional point of view. I don't want to take the 4-dimensional point of view right now, just so that we don't get confused.
It's related to the mixture. Sorry.
Yeah, of the 3 and 4-dimensional cosmological. If you fix one of them, then the other one is the 3-dimensional cosmological.
Right. So you fix the cosmological constant in the 4D.
Yeah.
And it's equal to a combination of the 3-dimensional constant plus this tension.
So you have two parameters, the 3-dimensional. Let's fix everything else. So the things we vary now are the 3-dimensional cosmological constant and the central charge. And let's just forget about the 4-dimensional picture for a moment. So you're saying, so what is in that language, what is the thing that I have to make small or large to have good control over the further quantum corrections?
Okay. So let me maybe write the equation so that I don't have to talk like this. think it's something like this. So this is something you fix.
Can you say it in words? Because I cannot
Yes,
read. It's
sorry.
too dark.
So this is the parameter related to the 4-dimensional constant. We fixed that.
I can't see what it is.
It's a cosmological constant of the 4D. It's minus L4 if you want.
Thank you.
This parameter here, it's the distance to the brain, aka the acceleration parameter, aka the tension of the brain. That is in competition, if you will, with the cosmological constant on the brain itself.
That's
Okay.
not quite what I'm asking. I understand that there is such a relation between the 3 and the 4-dimensional cosmological constants and the brain tangent.
Yeah.
I'm asking in the 3-dimensional language alone, what do I have to dial the mass, and what do I have to dial the smallness of the further quantum corrections? In terms of quantities that would appear in a 3-dimensional discussion.
So the mass, well, how do I say this? So the mu parameter, basically it sets the state of the CFT, if you will. In the 4D, it looks like a black hole. That's how you actually fix the stress tensor, by assuming regularity in the bulk. That's one thing. And that doesn't really play a big role. The big role is played by L, which I believe is gonna transfer in the large cosmological constant of the sitter. If that's what you meant. So it's a very small L. It's close to the boundary. That's the linear regime that I want to have in this sense. Well, let me do it here because it's the same thing. So this distance here is L.
Again, if possible, could we talk about 3-dimensional objects?
Well,
This
I
is a
said that
4-dimensional.
you tune basically the 3-dimensional cosmological constant of the sitter to be very large. I believe that's the correct way
Compared to
to say
what?
it. In such a way so that you fix the 4-dimensional constant. I mean, I don't know exactly what is it that's.
All right, let's talk offline about it.
Okay, yeah. Sorry. I guess it's gonna be easier with equations. Yes.
So coming to the picture at the end, the speculative picture.
My favorite.
Yeah, so I get this tendency to imagine that there is a crunch singularity when the brain hits the boundary that starts there. So that would affect the domain of definition of your Uber Euclidean CFT, no?
Okay, so that's obviously something that has been on my mind since we've heard about it. However, the usual arguments for why one would say that there's a crunch singularity, I'm not really sure that they apply here. And it's a little bit subtle, so I can explain it later. But basically, the setups are not exactly the same. So one is the setup.
Okay, I'm just imagining that I make the brain with scalar fields.
Yeah.
And then you get the standard crunch situation. No?
I know what you mean. It's
Like in Coleman-de-Lucia type.
It's Coleman-de-Lucia, but it's not exactly Coleman-de-Lucia. Because in Coleman-de-Lucia, what they have is a sort of a, it's a true vacuum of ADS expanding in the false vacuum, which is a Minkowski spacetime. Here, we don't have such a Minkowski spacetime. We just have this cutout of the brain. We basically just have nothing as the false vacuum. And that sort of interferes with the theorem that they proved in the follow-up paper that actually shows that there are trapped surfaces and so forth forming and the crunch singularity therefore emerging. So I'm not sure yet what is the resolution of this, but at least I can say for sure that that paper cannot be applied directly here. But we can maybe discuss a little bit more later. Yeah.
Okay.
Well, if there are no more questions, let's thank Marija again for an excellent